Thanks for the organizers to put together this event. I'm here for the first time. I already love it. So my title is about joint work with Achim Krause and Jonas McCandless. And most of the results I'm going to talk about, we worked out 3 years ago. But there's this one ingredient which I learned recently from Kaledin, and which I'm very excited about, which is about how to do genuine homotopy theory for infinite groups, and that's what I mostly want to be talking about. But let me first set up the stage and tell you a little bit about our motivation. And that is, if R is a ring, and say an ordinary ring or ring spectrum, there's this invariant called topological Hochschild homology R. That's among other things a spectrum, but it has more structure, which has, it's very important. It's what is called a cyclotomic spectrum. And what that means, it's in particular, it has an action by the group S1. And there's this map we call the Frobenius, which is a map from THHR to THHR Tate CP. That's the Tate valued Frobenius of the spectrum THH. And that's basically what it means to be a cyclotomic spectrum, to have an S1 action in such a map. And one of the consequences of having that structure is that we get a primary invariant of such a cyclotomic spectrum, that's TC. And once you know what cyclotomic spectra are, it's pretty easy to define TC. It just maps out of the sphere into THHR as a spectrum in the category of cyclotomic spectra. That's what TC is. And that story I think we understand well, and that has been used a lot in K-theory computations and so on. But there's also this variant of TC, which is if on top of a ring you have a bimodule. So M is going to be an R bimodule. Right, and of course this also makes sense for ring spectra. Then there's this thing called THH with coefficients, in M. It somehow fades out. Huh? Slowly. So there's a thing called THH-R with coefficients in M. And I guess I haven't told you how to define THH, but there's a bunch of different equivalent definitions of THH. One is through the cyclic bar construction. So what is THH with coefficients? Just put M here, and then you put M tensor R. There are two maps, the action from the right and the action from the left. And then, this extends canonically to a simplicial object like this. And so on, and then you take the geometric realization of that. And I guess here you really consider all these bimodules and rings and so on as spectra. So we're tensoring over the sphere here. So that's one definition. And another one is that you just tensor M over R tensor R up with R. Anyway, so this is a well-known invariant of a ring and a bimodule, and it's THH with coefficients. And now the question is on THH without coefficients, which is recovered by setting M to be R, we have the cyclotomic structure. And a basic question we've been asked ourselves is what is the structure that THH with coefficients possesses? What is kind of left of the cyclotomic structure possesses? What's left of the cyclotomic structure on THH for THH with coefficients? And actually, I guess a sort of related question, what are the primary invariants we can do for THH with coefficients? And of course, one of the reasons that THH has an S1 action, if we sort of do THH through the cyclic bar construction, that would just end up happening that I replace M by R. Right, and then what you have is you have a flip action of the group with two elements here. And here you have an action of the group with the cyclic group with three elements, permuting the factors and so on and so forth. And that is, this ends up being a cyclic object, and that is what Con has explained to us leads to an S1 action on the realization. But so here, we don't have anything of that sort left, right? There's no hope a priori that we have something like an S1 action on THHR with coefficients in M. And then, the the next question is, what would the Frobenius even be? Because somehow, I mean, you know, like having a Frobenius in particular involves something like the Tate construction for an action of CP. So if there's no S1 action, it wouldn't even make sense to say that. And let me tell you what the answer is. So here's the theorem, and I mean, I put our names because we prove it in this precise form, but I mean, this has been considered long before, of course. Oh shit. It's a bit of an IQ test. So, I mean, one answer is there are maps like this, THH Rm, and then the Frobenius phi p, for every prime p, there's a map like this. And the target is another R bimodule, namely what you can do is you can tensor M p times with itself over R. But that's again going to be a bimodule. From the left and right, you sort of eat up all the inner factors to form this tensor product. And then we form Tate CP here. And that's already a funny thing here, because how do you form Tate here? Because, you know, you think like a priori, this p-fold tensor product, this has an action by the group with p elements, the cyclic group with p elements, but the problem is this is not an action through R bimodules, right? Because, I mean, there's a problem with the left and the right action. So part of the statement is that this actually does support a well-defined CP action, and then there's a map like this. And more precisely, these turn THH Rm into what we call a polygonic spectrum. Into a polygonic spectrum. And so let me tell you what a polygonic spectrum is. Oh, only one can be operated at a time, apparently. Right, so what is a polygonic spectrum? Polygonic spectrum is the following definition. A polygonic spectrum is given by a sequence of spectra xn, and that's a spectrum with Cn action. So that's just my notation for functors from BCn to spectra. Spectrum with a Cn action in the most naive sense. For every n larger or equal 1, together with maps with this Frobenius map from xn into xpn, Tate CP, which I call phi p. For every n larger or equal 1, every p prime, which are Cn equivariant. Right, so that's the definition. And let me say one word. I mean, first of all, of course, I have like not said any word about the Tate construction, so I'm not going to. Like, that was kind of my implicit plan. I hope like everyone has seen the Tate construction or an idea what it is. If I have, I mean, this guy by definition, this is p times n. This guy by definition has an action of the cyclic group with p times n elements. So if I take Tate with respect to Cp, I have a residual Cn action, right? Because Cpn mod Cp is Cn, and that's how I make this a Cn spectrum. And so this map is supposed to be Cn equivariant.
Is it important that p is prime?
Hmm?
Is it important that p P is prime?
Yes. Yes, absolutely.
Doesn't the trivial map induce the trivial Polygonic spectrum?
The trivial map, as in, you mean?
What's the statement of the theorem?
The statement, I mean, so I guess you're asking whether I could just take the zero map?
Yeah, I mean, that's the map that does that.
Yes,
What's
so.
the statement of the theorem? No, I'm sorry, it's a honest question.
No, I mean, like, I guess, let me see. So I guess you're right that I could always take the zero map. I guess the statement of the theorem is that there is this map, canonically and natural in R and M, such that if M is equals R, it reduces to the non-trivial map on THH. Yes, absolutely. So, I mean, I guess maybe I could sort of say as a somewhat canonical natural map, but yes, good call. Okay, I'm not going to get out of this, so I think. Yes, good call. Thanks. Okay, so right, so that's the definition of a polygonic spectrum, and that's kind of what I want to isolate about properties about. And of course, once I have this definition, then I can form a category of those, which we denote polygonic spectra. Or sometimes we have this fancy notation where you put this little polygon here. That's the category of such, the infinity category of such. And I mean, why the name polygonic, by the way? So a cyclotomic spectrum just in some sense has a single xn, right? Like it's like a polygonic spectra, but all the xn are the same, and then we have a single map and an S1 action. So the way I think about like a cyclotomic spectrum, it assigns something to the circle, and then you have a rule. So the maps give you some sort of rule what happens if I sort of like dissect the circle into like primes, right? I dissect the circle, I put like p dots on the circle, and the cyclotomic structure gives me a way of doing that. And in the same way, I think about a polygonic spectrum as assigning something to every polygon, every n-gon. And then again, like I have these coverings or dissections of n-gons, where I sort of think of like the p n-gon as a sort of p-fold dissection or covering of the n-gon. And then I get sort of rules associated to that. That's where the name polygonic comes from. And finally, of course, what I can do is I can, I can now define like a fundamental invariant. Once I have like singled out the category in which I want my invariants to live, I have this fundamental invariant, which is TR. So X is going to be one of these polygonic spectra. And what I'm going to do is I'm going to define this to be just a mapping space in polygonic spectra from the sphere into X. And I guess in order for this to make sense, I first have to tell you what the sphere is at the polygonic spectrum. And this is like very trivial. It's just the polygonic spectrum where all xn are the sphere itself. And all the maps, and now I guess I have to be a bit careful, all the maps are the canonical, I mean the action is the trivial action. And then there's always a canonical map from the sphere to the Tate CP for the trivial action, a non-trivial map, I guess. For example, the unit of the ring structure on the sphere Tate CP, or the non-trivial map which factors through the homotopy fixed points. So that's a non-trivial polygonic structure on the sphere, and then I define TR to be this mapping spectrum. And similar to cyclotomic spectra, I can work out what that is. This is actually a huge equalizer of product n larger equal 1, and then xn hcn, and then you have these two maps into, here you form a huge product over numbers and primes. And then you do something like xpn to the Tate CP, and then homotopy fixed points for Cn. And it turns out there's two maps. One map is maybe called the Can map, and one map is called phi. And the Can map basically comes from the projection, like from xn hcpn, you can project to xpn Tate CP hcn. It comes from the projection from the homotopy fixed points to the Tate on the inside, and the other one is induced by the map phi. Okay, so that's one definition of TR of such guys, and then of course once I have that I can define TR R comma M for a ring and a bimodule just to be TR of this polygonic spectrum with this like non-trivial phi p maps, and of course then the classical TR of a ring, this can be defined as just TR of a ring with itself considered as a bimodule. I mean the ring considered as a bimodule over itself. Okay, good. So that's the setup. And am I supposed to not write on this board, Christian? Can I write on this board? Yeah. Okay. Good. So okay. So what's the statement? So maybe here's a theorem with a little bit of more content about this like definition of TR, and this is like. Let me just. I mean, the first one is maybe a little bit fishy. So this agrees with the old definitions. So there have been like a lot of definitions of TR in the literature, and the claim is that this agrees like under the appropriate equivalences with those. I guess, I mean, for ordinary rings or ring spectra, this is basically a consequence of what I've done with Peter. Then I guess there's other definitions which we compare in the paper with Achim and Jonas. And finally, I should say, I mean, the first instance that I'm aware of in the literature where people have defined TR with coefficients, that is Linton-Strauss-McCarthy. I mean, I might be wrong on that, but I hope this is the first one. And so one can compare it also to Linton-Strauss-McCarthy. So I'm just putting their name here, because I think it was their insight that you can actually define something like TR with coefficients. Because a priori, as I said at the beginning, like this is very surprising that something like TR with coefficients exists, given that THH with coefficients does not support any cyclotomic structure. So that's kind of, I think, their insight that it does exist. And so all of these definitions agree. So this gives us a bit of a more homotopy invariant construction of TR with coefficients. What is the second statement of the theorem? This is pi naught of TR with coefficients for a ring, as well as in a bimodule. This is isomorphic to some explicit algebraic construction, which is denoted WRM. This is Witt vectors with coefficients. With coefficients. And it's big Witt vectors for the experts in the room who know like there's p-typical Witt vectors and this is big Witt vectors. Or like maybe I personally would like to call it global Witt vectors because it's like p-typical for all primes. And I guess we've given an explicit algebraic construction of that in work with Emanuele Dotto, Achim Krause, and Irakli Pachkoria. And let me maybe not get into how to explicitly construct this. This is a funny thing because, you know, like here I never said, for example, that the ring has to be commutative. So if you let R be a non-commutative ring, this is like Witt vectors for non-commutative rings. And usually if you see Witt vectors, it's only like done for commutative rings and p-typical and using very specific arithmetic properties. So this shows you that Witt vectors is some super general construction. And I think already Witt has like observed that if R is a commutative ring, he gave this like beautiful description of Witt vectors is what we generalize here, which is till to date my favorite construction. It's kind of, you just, I mean, you know, if R is a commutative ring, then Witt vectors is again like a ring. But let's ignore that for the moment and just consider it as an abelian group because, I mean, TR was just a spectrum. So what is it as an abelian group? Then it's just somehow you take power series with leading coefficient 1 over that ring, and that is a group under multiplication. So the additive group of Witt vectors of that ring is just a multiplicative group of power series with leading coefficient 1. And that's my favorite description of like the ring of Witt vectors, so the ring of big Witt vectors. And all the p-typical ones are quotients of that. And I want to use this description in a second to explain some aspects of the theory. Okay, anyway, so we understand pretty well what pi naught of TR is by means of these Witt vectors. And this, by the way, holds like for every connective ring spectrum and every connective module, but it will only depend on pi naught anyways. Okay, so that is...
Can you slightly lower the little blur because it obscures?
Yes, sorry.
Do you have connectivity assumptions in part 1 of the theorem?
No, but we have some... I mean, this depends a little bit on which old definition you want to compare it to. If you want to compare it to the actual, like, sort of point set model they write down, then yes, I think you're right that we have some sort of... the conditions are like model dependent, yes. Yeah, yeah. So I think there is a condition in terms of the explicit, like, pre-spectrum you write down, but sort of, I think it has no invariant meaning, so to say. Like, you can always replace anything by something which satisfies this condition up to weak equivalence. That's what. No. Oh, sorry, yes. Oh, yes. That's what you meant. Yes. Sorry. Yes, absolutely. Yeah, good call. Sorry. Yes. Yes, good call. If R and M are bounded below, so R connective, M bounded below. Sorry. Yeah, sorry, absolutely. I was so much into our, like, we also gave a definition of TR and it agrees unconditional with that, but this of course doesn't agree unconditional with the old ones. Yes, thanks. Okay, so.
Can I also ask about this TR? From this description in terms of mapping spaces,
yes.
It looks like if you do the polygonic thing to a cyclotomic spectrum, you should get TC instead of TR. Can you explain why that's wrong?
Yes, maybe I want to explicitly say that, say what happens as part 4 of my theorem, if you bear with me, and then if you're not happy after that, please feel free to ask again, okay? Right, so maybe a third thing I want to say, which is also the observation of Lindenstrauss-McCarthy, and I guess also Dundas-McCarthy, is that you can describe explicitly TR blank. That's a functor which eats an R bimodule and produces a spectrum. And the statement is that this is the limit of the Goodwillie tower. Of another functor, which is K-theory with coefficients. Let me maybe write it as cyclic K-theory of R with coefficients in M. Right. So you can consider this functor, like, K-theory with coefficients is basically, or K-theory of endomorphism sometimes called. I call it cyclic K-theory. And I guess somehow the identification of the first derivative is Dundas-McCarthy. And then, the whole thing is Lindenstrauss-McCarthy. And somehow, if you have this formula, it's actually not so bad. Because from this equalizer formula, you can very easily construct a tower, or like from sort of thinking about truncating the ends, you can get a tower, the TRN tower, and it's super easy to identify the associated graded. And once you know the first derivative is THH, it's actually easy to also identify the higher derivatives. So this theorem somehow with this definition becomes easy except for the identifying the first derivative, which is Dundas-McCarthy's famous theorem. Okay, so that's, I think, a very nice way of seeing what TR abstractly is. And then this gives you like a very concrete algebraic model. So in principle, the game should be to sort of identify, play out the two perspectives against each other. And here's part 4 of that theorem, that is the functor. I guess this is kind of what the question just was. If I just have a cyclotomic spectrum, which remember is a single spectrum with an S1 action and these maps phi p, I can consider this, or like this gives rise to a polygonic spectrum. What does this functor do? This will just assign, like, the cyclotomic spectrum will make a constant polygonic spectrum, so to say. Every xn is just x. I just gradually forget part of the S1 action, right? And in step n, I'm just remembering the action of the cyclic group of like n's roots. I gradually forget that stuff, and the Frobenius just stays always somehow the same under these identifications. So there's an obvious forgetful functor. And so the statement is it has two adjoints. I guess the left adjoint L and the right adjoint R. And we have formulas for those. And that is L of I of X. So X is going to be a cyclotomic spectrum. So I first apply I and then L. And the formula is that this is given by X tensored THH of sphere adjoint X. So that's a sort of just like the spherical polynomial ring. In other words, the suspension spectrum of the natural numbers. And I want to do the reduced one. So this guy modulo THH of the sphere. And what is the formula for the right adjoint? And I guess, I mean, I'm strictly speaking not giving you formulas for the adjoints. I'm just giving you formulas for like the composites here, which is a little bit easier to write down. We can also give formulas for the adjoints. And this is going to be the inverse limit over omega of X tensor THH Sx mod X to the n. Okay, so these are the formulas. I hope these formulas make sense, and I guess I forgot a reduced here as well. Yes, n tends to infinity. And I should mention a couple of things. I mean, first of all, these formulas are very easy to obtain because basically this is just about like here I have an S1 action and here I have Cn actions, and then we know like the adjoints, you know, like it's clear if you have an S1 action you can restrict to a Cn action, and the adjoints are given by induction and co-induction. So now basically from that and playing a little bit around with Frobenius, you just see those formulas. These are like straightforward once you have the categories. Second remark is this limit is like brutal, because this is a limit in the category of cyclotomic spectra, and these are like insane. But okay, you just from abstract nonsense get that there exists such a limit. Whatever it means on underlying spectra is totally unclear. Okay, so I mean, but it doesn't matter, fortunately. And now I guess I can say like how like TR relates to TC using these adjunctions. Now somehow, maybe I'm gonna write there. That's a good place. Okay, so here's an easy corollary of that stuff. Corollary. So let's work out what TR of R is. So remember, TR of R is just TR of R comma M, where M is equal to R. Right, so what it really is actually, we just do TR of which polygonic spectrum? It's a polygonic spectrum which is I of THHR. Right, so I just consider THHR as a cyclotomic spectrum and then forget the cyclotomic structure. That's basically by definition or by a theorem I had there, this is what it is. And now this is now just maps in polygonic spectra from the sphere, which is also I of the sphere. So the sphere also happens to be a cyclotomic spectrum, which I forget down, into I THHR. So that's what TR is. And now I can play around with my adjunctions. So now, first adjunction, I use that, this is I. So I can sort of pull over the left adjoint here. So this is going to be maps in cyclotomic spectra from the left adjoint here. Now we look up the formula there, it's Li of the sphere. So it's going to be THH reduced of Sx into THHR. So that's one formula we immediately get for TR. And this formula, I think initially, to my knowledge, is due to Blumberg-Mandel. The fact that on the category of cyclotomic spectra, TR is just co-represented by the cyclotomic spectrum THH of the polynomial ring. But okay, so now we can also, so that's one formula, but let's also play the other game, right? I mean, we still have two i's, we can also pull over this I to the right. So what do we get there? Then it's also equivalent to maps in cyclotomic spectra from the sphere into the right adjoint pulled out here. So right, so let me write it R I THHR. And now we look up the formula for the right adjoint. And fortunately, I guess now, this is a complicated limit, but it's a limit in cyclotomic spectrum, and we're mapping a cyclotomic spectrum in. So the limit comes out to become a limit. So this is going to be, and the omega, of course, comes out. So it's going to be omega of the inverse limit. And now what we have is we have to take THHR and tensor it with this THH as x mod x to the n. So it's going to be THH, mapped from the sphere into that. So it's going to be TC of Rx mod x to the n, reduced. And that's, I mean, the fact that this is true is initially a theorem of Bentley-Schlichtgrull. And I guess sort of highly inspired by considerations of Spencer-Bloch. Before like this whole TC machinery and stuff was invented, I mean, this is actually ends up being equivalent to K-theory of Rx mod x to the n by Dundas, Goodwillie, McCarthy. And so this is how Spencer-Bloch initially defined TR, like back in the day, before like all this TC stuff was invented. And then I guess Hesselholt for FP algebras and later Bentley-Schlichtgrull proved that this agrees with actual TR. And so that's a theorem of theirs, and I guess I should say Jonas McCandless proved this for ring spectra. Bentley-Schlichtgrull only proved it for ordinary rings, and Jonas McCandless then proved this formula for TR for the stuff. Okay, and so here I think like maybe I hope this answers the question. So now what you see, what you have to do is you have to sort of, there's a huge difference between computing mapping spaces in here or mapping spectra and mapping spectra in here. And this adjunction exactly tells you what the difference is. Okay, so that is what I wanted to say about this abstract category. And here now I want to come to the actual question of the talk. This is maybe, now that I've isolated properties that THH with coefficients has, the question is, I mean, this had somehow canonically, I mean, once you correctly identify the structure, this gives you canonical definition of TR with coefficients. And the next question is maybe, what structure does TR with coefficients carry? Right, I mean, it used to be a mapping space and polygonic spectra, but what additional structure do we have? And here's one answer. And I guess, disclaimer, I'm probably, again, going to allow the zero map. But let me try to say it like in a way that, yeah, I don't know how to repair that now. There are canonical non-zero maps, non-always zero maps. One is called the Frobenius, and that's a map Fn, and it goes from TR, R with coefficients in M, and now similar to the map on THH, I have a map into the p-fold tensor product of M, and then HCP. And again, it's not clear a priori that this guy has a CP action. So that's a result of similar nature. So that's a Frobenius map, and then there's a Verschiebung map. Vn for every n from TH8 TR R with p-fold tensor product HCP into TR R. Yes, yes. I think I mean n and cn. Now I mean n and cn. And here it turns out that I can sort of write n and I have to write n. Whereas at the beginning I wanted to write p. The reason is that here I'm taking homotopy fixed points and homotopy orbits, and they behave different than the Tate construction with respect to primary decomposition. Okay, so that's part of that's the statement, and maybe I can say, okay, so here's one thing I can say. We had this isomorphism between pi naught of TR and the Witt vectors. Oh, that was my cell phone, shit. Pi naught of the Witt vectors, and I guess, where is it? Whatever. And on this, like, it's the width vector Frobenius and the width vector Verschiebung. Right, so that, for example, it says on pi naught it's not the zero map. Okay, and I guess the question is like, these of course have to satisfy algebraic relations. So for those people who know Dieudonné or Cartier modules, one of the relations you have on the width vectors is that Frobenius after Verschiebung is multiplication by n, and then like the n Frobenius commutes with the m Frobenius, and the n Frobenius commutes with the m Verschiebung as long as n and m are coprime. And there are all these relations between these maps, and sort of one of the questions, how do you like sort of coherently say what these maps have to satisfy? And there like equivariant homotopy theory comes to help. And so let me just recall what a genuine G spectrum is. G is any group. And I mean, G is going to be the integers for me in a second. So the group is supposed to be a discrete group, but infinite. And then there's this category of genuine G spectra. And I want to say finite genuine G spectra. And I mean, I should probably write cofinite, following the usual terminology of equivariant homotopy theory, because the kind of subgroups I want to consider are those whose quotient is finite. Let me just, I mean, this might be confusing, but let me just go with like the fact that the orbits then are finite. That's why I'm writing finite here. And so what is this? Like one way of writing this, following like, I guess, work of May, Guillou, and later Clark and his collaborators, is that we can write this as additive functors, this category, from the category of spans of finite G sets into spectra. Right, what is finite G sets? Just, I mean, I guess finite sets with an action of G, so necessarily all orbits are going to be finite, so the isotropy groups are going to be cofinite. And then we just take the span category of that, that's an infinity 1 category, it ends up being semi-additive, so coproducts and products agree, and then we just take additive functors. The stuff that send disjoint unions of like finite G sets to products of spectra. That's a kind of one model for equivariant homotopy theory. And then you can prove the following result. There is a finite genuine Z spectrum, by which I mean one of those guys, which I call TRRM underbar, with the following. So the fixed points. So what fixed points am I allowed to take? Maybe I sort of make the underbar a little shorter. If I have one of those guys, I'm allowed to take fixed points with respect to all cofinite subgroups of the integers. These are, of course, all nz for n larger equal to 1. So, you know, this is the evaluation of this functor. This is like usually written upstairs and with the subgroup. I guess this is confusing if you have never seen this, but like this is how the notation goes in equivariant homotopy theory. And so the claim is that this is actually TR R, n-fold tensor product. And then, I mean, moreover, the F, the map I have over there, this corresponds to the so-called restriction. And the V is actually the transfer. But, right, in equivariant homotopy theory, sort of for every map of like subgroups, you can restrict from a bigger subgroup to a smaller one, and you can transfer the other way around. That's what sort of the structure of a genuine spectrum encodes. And yes?
Does this only depend on profinite completion of G discarded model?
Yes. This only depends on the profinite completion. You're absolutely right. So maybe in some sense it would be more canonical to write this whole thing as the category of genuine spectra for the profinite group C hat. Except there's one problem, which is, you know, I mean, this doesn't matter at all here, but like if you have a non-finitely generated group and you profinitely complete it, then the topology on this profinite completion is not the profinite topology. So, I don't know, let that sink in, that statement. You know, like there's on every group we have a profinite topology corresponding to cofinite subgroups. And it's not true that the topology on a profinite completion of a group is the profinite topology. So that means like this.
Don't go to the completion.
Hmm?
The profinite structure.
Yes, absolutely, you're right. So I could more generally sort of give myself some topological group or some sort of group with a profinite substructure, and that's, I mean, I decided not to for this talk, but yes, absolutely. Can get rid of these problems, but that's why for the moment, I didn't want to write. But I think, yeah, I don't know. It's just not an idempotent functor, this profinite completion, unless you set it up in the right category. Oh man, this erasing doesn't work at all. Huh? Oh yeah, that's it. I take my time. That's good. Okay, so let's see. Part of the statement is the coherence I have for my Frobenius and Verschiebung map are exactly like sort of they form a functor on this kind of category. So they are genuine G spectrum. And maybe now can write a slightly more general statement. Of course, this doesn't only work for THH R, M, but for any arbitrary polygonic spectrum. I can do this kind of stuff, and this is like more generally, there is an adjunction so what you can do is you have this category of polygonic spectra, and then there's this functor TR, and this goes to these spectra Z finitely genuine, and then there's a functor the other way around, and that's actually geometric fixed points. So there's a functor called geometric fixed points in equivariant homotopy theory, and this functor just takes geometric fixed points of one of those guys, and this is exactly how you get a polygonic spectrum. And then on geometric fixed points you have these like Tady maps, and those are the ones. Okay, and this is actually how we prove this whole stuff, like namely, so maybe I should say this is geometric fixed points. This is how you prove the part about TR underbar having this structure. You just write down this functor, and you, by abstract nonsense, deduce it has a right adjoint, and then you figure out what the fixed points of the right adjoint are. That's how you prove this stuff, that these maps satisfy this coherence. And now there's a problem. So the story is beautiful as it is until now. But, I shouldn't like. I like it. Somehow it works out the easy way you would hope the story works out. And now you hit a problem. So I guess I've proven in my work with Ben and Peter before that something like that also works for cyclotomic spectra, but only in the p-typical case. And now we hit a problem, and sort of let me describe this problem. So the problem is this is not all structure on TR. And this is a little bit vague, so let me maybe substantiate what I mean by that. So I claim that this finitely genuine Z spectrum doesn't see all the structure we want to be. And the first problem is that geometric fixed points, like if let me go back to setting of an arbitrary group, that the geometric fixed points functors from the spectra, you have all these geometric fixed points corresponding to subgroups. These are functors to spectra. And now I can do them for cofinite subgroups. And for those of you who know equivariant homotopy theory, for finite groups, these are conservative. You can test equivalences on geometric fixed points. That's a consequence of isotropy separation. And the way you prove this, you use the isotropy separation sequence and you do an induction over order of subgroups. But of course, if I'm infinite, I can't start this induction. And so as a matter of fact, these are not conservative. And that's a bit of a problem because somehow, like the way these genuine spectra come up, they're geared toward like us having an understanding of geometric fixed points. And if we can't test equivalences or anything on geometric fixed points, we're screwed. So that's, somehow maybe the first thing that happens. And I guess more precisely, what I wish to be true and is not true is that the co-unit of the adjunction, so TR underbar of a polygonic spectrum, and then I take the geometric fixed points for like a subgroup NZ. This canonically maps through the co-unit to Xn, and this is not an equivalence. And maybe I can give you an example why this happens. So how do you see that? This is a very concrete problem with completion. Sorry, I should sort of maybe prove my... shit. This is a very concrete problem. So if R is a commutative ring, what happens is we can consider X to be THH R. And then we can consider what happens on pi naught. So the right-hand side will be THH R, so pi naught is going to be the ring itself. What is the left-hand side? I guess I haven't told you what geometric fixed points are, so let me tell you what the left-hand side is. TR is the width vectors of R, so n is equal 1. And then what's the left-hand side? It does quotient by transfers from like subgroups. So what you do is you quotient by those power series of the form P of t to the n, where n is larger equal 2. But this is an algebraic quotient. Right, and now here I give you like arbitrary power series, modulo those power series, which start with a t to the n and so on. And you see this is a canonical map here is not an iso. Just because you're somehow missing the topology, the t-adic topology on the width vectors. What you want to do is you want to write an arbitrary power series as an infinite product of those guys starting with t to the n. You need infinite products to do that. And you can't do that if you're just considering like algebraic operations. So in some sense, this kind of like, genuine structure doesn't see the sort of correct topology on the width vectors. That's part of the problem. And that's a problem I had like, 3-4 years ago, and I always like thought this must be solved by remembering somehow in some sense, categorical sense, the topology on the width vectors or on TR in order to be able to reconstruct THH. And I had all sorts of wild ideas how to do that using condensed mathematics and sort of pro objects and so on and so forth. And I could not somehow figure this out until like beginning of the, or like actually two months ago I had Dimitri Kaledin visiting. And it turns out he had figured this out like back in 2014. It's a remarkable paper. I've read it like 5 times. I didn't understand a single word, but after I worked it out and he explained it to me like it was all there. It's called Mackie Pro Functors, and I mean, this is a remarkable paper also because of the acknowledgements where he sort of thanks all Ukrainian people for their bravery in the fight against their barbaric neighbor. So, and that's why he told me he never published the paper because he can't make use of it, him being in Russia and sort of can't use it for any grant applications or anything because of that acknowledgements. Anyways, I think we should read it. It's a brave maneuver in 2014. Okay, so here's the definition that comes to help. And this is following, it turns out, Dress-Siebeneicher had also worked this out. Dress-Siebeneicher and Kaledin. Okay, so what's going on? So a G set S is called quasi-finite or almost finite if so all orbits are finite. Right, any G set will decompose into orbits, and I'm saying all orbits are finite, or other words, all isotropic groups are cofinite, and all fixed points are finite. That means there's only finitely many orbit types for each isotropic group. And then, of course, once you have that in place, you can define a sort of bigger model, bigger version, which we call quasi-finitely genuine spectra. And this is just very additive functors. I'm going to say what very additive means from span of quasi-finite G sets into spectra. Very additive means the following. If I have a functor from the span category, E, then what I want to say is like its evaluation on a disjoint union, this can be infinite. This, with the canonical map to the product, is an equivalence. Right, like additive would be this condition for finite decompositions, and I'm asking it for arbitrary decompositions. Right, so. And the claim is these are the correct structures we see here. Let me maybe substantiate what that why and what that means for the integers. So what's the example? Example, g is equal to the integers. And then, I mean, for example, when is such an infinite union, disjoint union, niz, I equals 1, when is this like quasi-finite? I mean, this is of course only if every ni somehow only happens like finitely many times. So if ni tends to infinity. Right, every ni can only happen like finitely many times, and you have a sequence of natural numbers, and every ni can only happen finitely many times. And then what is this category of quasi-finitely genuine Z spectra? That consists of, I mean, first of all, every such quasi-finitely genuine spectrum has a sort of underlying genuine spectrum in the sense defined before. I mean, first finite Z spectrum. So in other words, we have all these fixed points, E and Z, and we have the transfers and restrictions. But then secondly, we have certain infinite transfers. So additional infinite style transfers. Namely, which ones? So what we have is something like an infinite sum of transfers from subgroups niz to z. And that's supposed to be a map from the product I equals 1 through infinity, e upper niz to ez, if ni tends to infinity. So the way I think about this is like, you know, we have these transfers from 1, we have these finite transfers from niz to z, just because ni is a subgroup of the whole group. And then somehow what the structure allows me is to form certain infinite sums of maps that I have, but only certain ones, not all ones. And let me sort of illustrate this in an example why we have this and why this is reasonable. So example of the example, I guess. So if R is commutative, that's my running example, then what I want to do is I want to form a spectrum E, all of whose fixed points are just the Witt vectors of R. So the claim that exists such an example, and I guess when I write an abelian group here, I mean the Eilenberg-MacLane spectrum of this abelian group. So really I'm giving a sort of Mackey functor in this perspective. And then, I mean, what is the restriction? The restrictions are all the Frobenius, the Witt vector Frobenius. The transfers are the, I guess, Verschiebung. And the thing is, in this power series perspective, Verschiebung is just the thing where you insert, like, you know, the nth Verschiebung just takes the power series, inserts t to the n as a new variable. So that's the easy map. And then, I mean, why do we have these infinite sums of transfers niz to z? So from where to where are these even maps? These are supposed to be maps from I equals 1 through infinity, Witt vectors R. And it's supposed to be a map into the Witt vectors. And what does this map do? Remember, I mean, we think of those as power series. So we have a bunch of power series, I equals 1 through infinity. And we're going to form a new power series. And here I'm going to take the infinite product, I equals 1 through infinity. And then I insert t to the ni, or in this power series. And now the thing is, this is an infinite power series, but because the t's raise, this converges, this infinite sum converges in the t-adic topology. And I'm saying infinite sum, but you know, like remember, it's a product because the sum operation, the additive structure on power series was the multiplication. Okay, so that is kind of what we have. And let me end stating the theorem. I feel like I'm wasting like my precious time. Can already start. Yeah. You know, we do this wet erasing in Germany, and I always think it's very good for the students in courses because that gives them time to think. But now it like eats up my time.
I think the real pros get squeegee and erase the same time.
Yeah, you know. Point taken. Right, so what did I want to state as a theorem? That's what we prove, but really, I mean, I guess I should attribute it to Kaledin. He does it over chain complexes as opposed to spectra in some different language, but first statement is if X is one of these polygonic spectra, not only does pi naught form one of these like fancy quasi-finite G spectra, but TR. The TR we had before, the stuff with the transfers and the restrictions, this really forms one of these fancy quasi-finitely genuine spectra. All the fixed points we had before, all the transfers and restrictions given by Frobenius and Verschiebung, they form that. Secondly, this is an abstract statement about like these quasi-finitely genuine spectra, the geometric fixed points functors. Phi h from quasi-finitely genuine spectra into spectra are jointly conservative. This is, as I say, an abstract statement about this new version of equivariant homotopy theory are jointly conservative on bounded below objects. Below objects. That's an abstract statement. Thirdly, there is an adjunction, or the adjunction. I guess again I have some sort of, and I guess I should say part of 2 is actually that one can give a reasonable definition of geometric fixed points. A priori it's maybe not clear what geometric fixed points are, but the statement is there is a definition which somehow generalizes everything we know and makes this work. And then we have this kind of third statement, is quasi-finitely genuine spectra. These geometric fixed points again give me one of our polygonic spectra, TR here. And so this is the statement, is an equivalence on bounded below objects. So in other words, the co-unit of this adjunction is an equivalence. And maybe I should stop here, but I want to add one more point, which is, I guess this means like sort of, for some of you have maybe seen my previous work with Ben Antio, we have done a version of that p-typically. This means all of that actually now works integrally. So here I'm talking about these polygonic spectra, but let me say there's a similar story for cyclotomic spectra, where this ends up giving an equivalence of cyclotomic spectra with some category of integral topological Cartier modules. And this allows to identify the heart. I mean, there's a sort of obvious T structure on cyclotomic spectra, and using this equivalence, you can sort of identify what the heart is. It's kind of an integral version of Cartier modules, or like integral Dieudonné modules, sometimes called, where again, like on an algebraic level, you have infinite sums of Verschiebung. And I mean, you can prove theorems of this sort. I mean, maybe I'm just teasering that. If this is why I was really after that, and this is something I can prove now. If R over K is a smooth K algebra, then you can do stuff like this. You can take THH R, and you can tensor it over THHK with something like pi naught in this T structure, the cyclotomic T structure on THHK. And then TR star of that is integrally isomorphic to the relative de Rham bit complex. And okay, so I end the statement here. Thanks very much.
Thanks a lot. We have time for a few questions.
First, okay. Do polygonic spectra admit a T structure like the
Yes.
T structure?
Yes, so polygonic spectra admit a T structure where the connective objects are those where all xn's are connective, the obvious one. And now you can wonder what does it correspond to on this side, and it corresponds to the ones where all the fixed points are connective. And so on polygonic spectra, it's very mysterious what the taking connective cover and heart means. But on this side, it's like super straightforward. You just literally sort of get Mackey functors on that category as a heart, right? Like functors from this category to abelian groups, yes. And the cool thing is you don't have any completeness. Somehow having these infinite sums, this already makes it complete, as it turns out, with respect to some topology. Yes, so this is true. And sort of, yeah, as I say, like I had tons of ideas how to say completeness correctly, and somehow, yeah, Kaledian just figured it out. It's just a functor in a certain category. Yes. Yes, so, okay, so what you have to do is you have to write down a formula for geometric fixed points. So I guess one way to define them is as a adjoint to inflation. Inflation, just strictly speaking, makes sense. And then you have to prove a formula like this. And here's the formula. Let me give you the formula. Phi h is going to be something like you take a cofiber. Here you have something like xh, the actual fixed point. So I want to define that for x being one of these funky, like quasi-finitely genuine spectra. And then it turns out here you have to take a co-limit, xk, or maybe let me write xs. And here S somehow runs through proper quasi-finite G sets. Proper. Where proper means, you know, proper isotropy. All isotropy is proper subgroups. And what you have to do is you have to interchange that co-limit with certain limits if you want to prove the statement. And bounded below, I mean, this is uniformly bounded below co-limit. And so.
They're all transfers, right? These maps are transfers.
Yes, all these maps are transfers. But I mean, in contrast to ordinary homotopy theory where you would just take like orbits, here I have to run over all quasi-finite sets. That's the difference. And yeah, so in the end, I guess bounded below has to do with interchanging this co-limit. So like, I guess an abstract statement is that this category is the inverse limit of the category of quotients of G, cofinite quotients of G, but the inverse limit along the functors which are geometric fixed points. That's another way of saying it. Sorry.
Okay, I think we should thank the speaker again there because there's a new talk.